Chapter 12, Section 4, Weather Analysis. After weather observations are gathered, meteorologists plot the data on a map using station models for individual cities or towns. A station model is a record of weather data for a particular site at a particular time. Meteorology symbols, such as the one shown in Figure 1215, are used to represent weather data in a station model. For a long, complete list of the symbols that meteorologists use to represent weather data, see Appendix E. A station model allows meteorologists to fit a large amount of data into a small space. This also gives meteorologists a uniform way of communicating weather data. You'll use station models and weather maps to forecast the weather in the Mapping GeoLab at the end of this chapter. Surface analysis. Station models provide information for individual sites. To plot data nationwide or globally, meteorologists use isopleths, which are lines that connect points of equal or contrast values. These values represent different weather variables such as pressure or temperature, lines of equal pressure. These values represent different weather variables such as pressure or temperature. Lines of equal pressure, for example, are called isobars. Lines of equal temperature are called isotherms. The lines themselves are similar to the contour lines of equal elevation that are studied in Chapter 2. Just as you can make inferences about elevation by studying contoured intervals on a map, you can also make inferences about weather by studying isobars or isotherms on a map. For instance, you can tell how fast wind is blowing in an area by noting how closely isobars are spaced. Isobars that are close together indicate a large pressure difference over a small area. A large pressure difference causes strong winds. Conversely, isobars that are spread far apart indicate a small pressure difference in pressure. Winds in these areas would be light, as shown in Figure 1216. Isobars also indicate the locations of high and low pressure systems. This information is especially grateful when combining with isotherms, which identify temperature gradients and consequently frontal systems. These isotherms, and station model data, meteorologists can analyze current weather conditions for a particular time and place. This is crucial information. Meteorologists must understand current weather conditions before they can move on to forecasting the weather. You'll learn more about isobars in the problem-solving lab on this page. Short-term forecasts. In the early days of weather forecasting, meteorologists simply observed current weather conditions, compared these conditions to those that had occurred a day or two before, and then extrapolated the changes a day or two into the future. The resulting positions of the weather system served as the basis of their forecasts. Weather forecasting, however, is too complicated to rely on extrapolating the past movements of weather systems. Weather systems change direction, speed, and intensity with time. These changes take place in response to change in the upper atmosphere, so a reliable forecast must analyze data from different levels in the atmosphere. Digital forecasts. The key to unlocking the forecast puzzle lies in the fact that atmosphere behaves much like a fluid. Thus, we can apply many of the same principles to the atmosphere as its variables, such as temperature, pressure, density, and so on, that we can apply to fluid. Furthermore, these principles can be expressed in mathematical equations to determine how atmospheric variables change with time. For meteorologists to solve these equations on a global to national level would take an impossibly large amount of time. Fortunately, high-speed computers can do the job. A forecast such as this that relies on a numerical data is shown as a digital forecast. Digital forecast is the main method used by modern meteorologists, for meteorologists to solve these equations on a global or national level would take an impossibly large amount of time. Fortunately, high-speed computers can do the job. A forecast such as this that relies on numerical data is known as a digital forecast. Digital forecast is the main method used by modern meteorologists, such as the one shown in Figure 1217. It is highly dependent on the density of the data available. Basically, the more data, the more accurate the forecast. Analog forecasts. Another type of forecast, an analog forecast, involves comparing current weather patterns to patterns that took place in the past. The assumption is that weather systems behave in a similar fashion. Analog forecasting is so called because meteorologists look for a pattern from the past that is analogs or similar to a current pattern. To ensure an accurate and analog forecast, meteorologists must find a past event that is similar to a current event through all levels of the atmosphere and also over a large area. This is the main drawback of Analog forecasting. Still, analog forecasting is useful for conducting monthly or seasonal forecasts, which are based mainly on the past behavior of cyclic weather patterns. Let's explore the lengths and weaknesses of long-term forecasts. Long-term forecasts, regardless of the forecasting methods used, all forecasts become less reliable when they attempt to predict long-term changes in the weather. Why? Even high-tech computers cannot change every factor that affects the weather. Recall the mountains, valleys, rivers, lakes, cities, and countless other features on Earth's surface affect the amount of heat absorbed in a particular location. This is, in turn, affects the pressure and therefore the wind of that area, which in turn affects clouds formation and virtually all other aspects of the weather. Over time, all these factors interact to create progressively more complicated scenarios. The most accurate and detailed forecasts are short-term in nature, as shown in Figure 1218. For hourly forecasts, extrapolation is a reliable forecasting method because the current weather is dominated by small-scale weather features that are readily observable by radar and satellite. Forecasts in the 1 to 3 day range, however, are no longer based on the movement of observed clouds and precipitation, which change by the hour. These forecasts are dependent on the behavior of large surface and upper level features such as low pressure systems. A 1 to 3 day forecast can somewhat accurately predict whether the day will be rainy or dry, and if rainy, when the precipitation will occur. At this range, however, the forecast will not be able to pinpoint an exact temperature or sky condition at a specific time. Accuracy declines with time. At the 4 to 7 day range, forecast must attempt to predict changes in surface weather systems based on circulation patterns throughout the troposphere and lower stratosphere. Meteorologists can eliminate each day's weather, but can offer little detail as to when or what exact weather conditions will occur. At the 1 to 2 week range, forecasts are based on changes in large-scale circulation patterns. Thus, these forecasts are vague and based mainly on analogous conditions. Long-term forecasts involving months and seasons are based largely on patterns of cycles. Several of these cycles, such as the one shown in Figure 1219, involve change in the atmosphere, ocean currents, and solar activity, all of which might be occurring at the same time. The key to future improvement in weather forecasts lies in identifying the main influences involved. Understanding these influences and how they interact are finally determine their ultimate effect on weather over progressively long periods of time.